Okay, so welcome back to another video. So here we want to solve for real solutions x with x greater than 0, such that we have this following algebraic equation. We have that the square root of x plus the square root of x plus the square root of x infinitely nested, so it's the nested radicals, is equal to x plus x divided by x plus x divided by x, and then so on. That's what's known as a continued fraction. So anybody that's played around with numbers and or any mathematicians out there that seen like a standard formula like something similar to this, I think they can already figure out like what that answer is without having to show the work. For anybody that actually doesn't know, then well, you've come to the right place. Typically when you solve nested radicals or continued fractions, the method follows that you set a variable equal to that equation and set it back to itself, because that way it's actually as a repeated iteration. Again, same thing applies for the continued fraction as well. So that's pretty much the standard method that we're going to do this. And so this is actually the solution. This has a very nice relationship. Again, anybody that's playing around with math can see where I'm going with this, but for anyone that doesn't, we'll get to that when we get to that. So let's actually just jump right in. So before I say anything further, there's actually two solutions we can actually solve this. Personally, I think the first one, how I'm going to solve this, is more of the uninteresting method, I like to say. But it's more of the second solution that we're going to solve that I think this like establishes more of like the, I guess, content that you guys want to see. So with that, so let's actually first establish that we can actually set the left-hand side. We're going to write this as the following. We'll put this as y is equal to the square root of x plus y, simply, and it works. So we just actually place this back in, so on and so forth. It's infinitely nested. So let's actually move on to the right-hand side and say that for here, if I let y, again, this is the equation that's equated to, so it's the same thing. So I'll put that as x and then plus x divided by y. Again, same thing. It just repeats the construction from over here. So now what I can do is now for some algebra that I can actually just square both sides. So I have y squared is equal to x plus y. And then for this side over here, I'll just multiply y to both sides. So that way we can get rid of the, the fraction from this thing over here. So we have y squared is equal to x times y, and then add this with x. So it's also worth noting that with the condition that x is strictly greater than 0, and it has to make sense because of the whole square root, so it's always, positive, that also had to imply that y has to also be strictly greater than 0 as well. A little just key information just to keep in mind there. Now with these y squares are both equal to each other, so I can actually just equate these equations together. So x plus y is equal to xy plus x. Subtract the x's from both sides, and so I have y is equal to x and then times y. Divide the y to both sides, and so therefore I have that x is equal to 1. So technically that is the solution for this equation over here, but again, that's the uninteresting procedure, and I like to show the interesting procedure, so that's what we're going to do from here on forward. So with that, let's actually now, so what I'm going to do from here is that we're actually going to set the left hand side of the equation. We're going to take this equation, so let me first put this as y squared, then I'm going to subtract the y, set that equal to x, and then with this equation, I'm going to put this back in for the right-hand side, specifically this piece over here. So that will actually make some things like come out very interesting with the, again, with the whole procedure. So that means we have y is equal to, so substitute for x, we have is y squared subtract y, and add this with, put this on the top back again, y squared subtract y, and then divided by y. So we can simplify stuff out, of course. So far we have y squared subtract y, and then add this. So the y will cancel from both top and bottom, so we're just left with y. Same thing from over here, that's gonna actually be -1. Simplify things out a little bit further, and so we have, so far we have that y is equal to y squared, and then subtract 1. So let me actually now put this on the top over here just to reestablish. Y is equal to y squared minus 1. So with some algebra, let's actually subtract y to both sides. So now I have y squared minus y minus 1 equals 0. So we have, a little typical quadratic expression equation that we can solve for. A little bit easier to see, but anybody that knows this format already knows what the solution is. But for those who don't, for people who don't know, then we'll put it this way. So we solve for y on its own, so we have y is equal to, just use the quadratic formula again. So I have, so -1, and then +1, so that will be a 1 at plus or minus the square root of 1 squared -1 squared specifically, that'll just become 1. And then -4 times 1 times -1, so there's going to be 1 plus 4. And all this being divided by 2 times 1. And so therefore we have that y is equal to 1 plus or minus the square root of 5 divided by 2. But keep in mind that we have that y has to be strictly greater than 0 with the because of the fact that we have that x is greater than 0 with the whole substitution. So we can actually exclude the 1 minus square root of 5 divided by 2 as that's a negative number. And so the only solution we have is that y is equal to 1 plus the square root of 5 divided by 2, aka the golden ratio number. That's nice. And so with this, now let's actually plug whatever we have found for y back into here. So we have that we find our solution x, that what we're trying to solve for. So that x equals y squared, or in other words, 1 plus the square root of 5 divided by 2 square. Then we subtract this with, again, 1 plus the square root of 5 divided by 2. Through some simple computations, let's simplify this out. So if I fold the top, then that means I have that this is 1 plus 2 times the square root of 5. And then square root of 5 times square root of 5 is just positive 5, and then divided by 4 since I just squared this. Then subtract, let me actually get a common denominator over here. So I'll just multiply the 2 to both the numerator and denominator. And so that'll give us 2 plus 2 times the square root of 5. And so if I just solve this out, let's see. 2 times square root of 5, that gets rid of each other. And then I have 1 plus 5 is 6, subtract 2 is 4, then 4 over 4. And so I have that x is going to equal just 1. And so with that, we actually found our solution. I mean, we already did to begin with, but this is more of the cooler, procedure. And it's nice that you'll notice that if I put this back in, again, that actually does give you the golden ratio number if you solve this out numerically for ones. And specifically, the right-hand side is a well-known fact about the whole representation of a golden ratio for the continued fraction. So there's a little bit interesting to see in all this. So yeah, that's pretty cool if you ask me.